Okay, so welcome everybody to this talk about deep learning in general and DeepLearning4j as an Eclipse project. This is talk for beginners, so the goal here is to give you some basic concept about the topic and some Java code to start your own experiments. So let's give some definition. With a pure artificial intelligence, the developer usually has to write an algorithm that takes an input, elaborate it, and gets an output. While when we start using the term learning, it means that we are providing the system lots of input-output pairs and let the system get the correlation between the two. And we can do this with statistical tools, like in machine learning, or with neural networks, with deep learning. In fact, deep learning is just a new trendy name for an old topic, which is neural networks. Today, in deep learning, we are still using the same old, let's say, artificial model of a biological neuron designed by McCulloch and Pitts in 1943. So where basically we have a weighted sum of inputs, and then we have a threshold. Well, we usually, let's get more in detail. We have inputs that can be pure inputs or maybe output from previous nodes that are basically turned on or turned off, so 0 or 1. And each one can contribute to turning on or turning off the next node, turning on with an excitatory connection, so a positive weight, or turning off, contribute to turning off with a inhibitory connection, so a negative weight. At the end, we have a weighted sum, and we apply not quite a threshold function, but an activation function, which can be a sigmoid, or there are many options for this. And now we have seen the model of a single node, but how can we assemble more nodes into a network? Well, generally, we organize them into layers. So we have the input layer, the output layer, and a number of hidden layers in between. Two typical tasks for neural networks are classification tasks and regression tasks. In classification tasks, we have only one turned on node in the output layer, the one that corresponds to the class that is associated with the input. While for regression tasks, we have a value into a range. Let's take a very, very simple training set, a set of data composed of 2 inputs and 1 output. Let's say the 2 inputs may be the temperature and the atmospherical pressure in a given day, and the output may be the rain millimeters forecast for the day after. It's just an example. So how can we train a network, a simple network composed of 2 inputs and 1 output, so 2 weights, against this training set? We can do like this. We can start with random weights, and then take the first item into from the training set, calculate the actual output. Then, since the weights were set randomly, most probably the current output will be different than the target output. So we have an error. And if we go through the whole training set, we can calculate a global error, which is associated with the set of weights where we started from. So in the end, we can see the error as a function in the weights domain. Well, this function, maybe it could be like this, but we don't see this function. We just have one goal in mind: to minimize the error. So our ideal goal is to find the global minimum of this function. But in practice, we don't know how to find this global error. We can just be happy to find a good minimum. Because what can we do? We can just move around in the weights domain, calculate the error, and then decide which to move next, in which direction, and how much I should move. Well, how much I should move, the step that I take, is usually known as the learning rate. And it is a very critical parameter for deep learning, because if the learning rate, so if the step is too large, then maybe I can skip the global minimum, or I can skip a good local minimum. While on the other hand, if the learning rate is too small, I could be too slow. I could stay in a bad local minimum forever. And what about the direction? Well, we can start in a random point in the weights domain, but we cannot move randomly in the weights domain. We have to apply some technique. Gradient descent is one of these techniques. And in particular, speaking of neural networks, there is the backpropagation rule, which is a variation of the gradient descent, which became famous in 1986 with this famous article on Nature magazine. And it consists basically of using the error to backpropagate changes in the weight domain back from the output layer back to the input layer. So that is the reason for the name. Let's speak about numbers. Let's say we have to deal with a classification task of images. Maybe we have 400 by 300 pixels images, so basically low resolution images. But instead, we have already here 120,000 input nodes. So let's say we put 50,000 nodes in the first hidden layer. We already have 6 billion connections, so 6 billion weights just between the input layer and the first hidden layer, basically for a very simple task. So big numbers. So you can imagine why in the history of the neural networks there were many dark ages, many difficult times. And why there is so much success now? Well, basically for two reasons. One, we have lots of data now. We have sensors, IoT, devices, internet, data everywhere. And, well, machines, PC, are much more powerful now than before. And why the term deep? Well, because it has been discovered that when a network has many hidden layers, the layers that are more distant from the input tends to detect more abstract features. What do I mean? Let's say we are speaking of image classification tasks. We usually see that the first layers tends to specialize in detecting lines and corners, while the layers after tends to use this feature to classify, to detect more complex shapes in a growing of abstraction. There are many degrees of freedom in this field. You will find yourself asking, how many hidden layers should I put? How many nodes should I put there? Which activation function should I use? What value for the learning rate? What kind of network? There are many, many choices. But one thing has the priority, and this is how I can map the input and output, the real case, from the real use case to the input like this, so 0, 1 nodes. Let's make an example. This is the MNIST dataset. This dataset is kind of considered the hello world in deep learning, so the initial example, and it is composed of 70,000 images, 28 by 28 pixels images, of handwritten 0 to 9 digits. How can we use this kind of image for a network? Well, for example, we can serialize all the pixels into one row of nodes. So in this case, we have 28 by 28, so 784 input nodes, 0, 1 nodes. Well, for the output is much easier because we just need 10 nodes, and then since it's a classification task, we have just to turn on the node that corresponds to the class. And the MNIST example is split like the, well, let's say, in general, a data set, we usually split a data set in two, a training set and a test set. The training set is used for the real training, while the test set is not part of the training, but is just used to measure how the network is learning. So in case of the MNIST example, the training set is composed of 60,000 items and test set 10,000. You can download there are many points on the internet where you can download this example, but for example, this is one of them. You can download the MNIST images. They look like that. So there is the two-folder testing and training, and each one has 0, 1 folders with and into the folders, there are the images, the samples. Oh, let's speak about DeepLearning4j. And because we want to use DeepLearning4j against that sample. DeepLearning4j is Java library, an open source Java library for deep learning. It is an Eclipse project, and it is very easy to use. For example, we can create with Eclipse a new Maven project, and we can just add these dependencies in order to use it. let's see an example. In this case, we are defining a set of constants that we will use later. And then we are preparing an helper method that will allow us to build the dataset iterator, the dataset iterator that will be used both for the training set and the test set. This is how we fill the body of this helper method. So we are using, let's see, here we are defining this native image loader, which is responsible to read the image and to serialize the value of the pixels. Then we have this scaler, which will be responsible to map each pixel value into a 0-1 range. And then we go through all the, well, we create two structures for the input and the output. So you can see that we have the number of samples, the total number of samples in the rows, and we have here the columns for the input and the columns for the output. We go through all the file system. We load each image and use this loader to read the image, the scaler, and use them to populate the input, and then we populate also the output with the label digit, with the classification. In the end, we package the input and output into this dataset object, and then build this dataset iterator. So this will be used both for the training set and the test set. So you can see here that we are using this helper method to get the dataset iterator. Then it's time to build our network. And this is how we build our network. We are adding, let's see the important points. Here we are adding 2 layers, and the first layer maps is between the input and the output. So we have a hidden layer of 1,000 nodes, and then this is the layer between the hidden 1,000 and the output 10. This is the final layer. Here is how we can train the network. So with this fit API, this will take quite a while for the training, but at the end, we can evaluate, build the dataset iterator from the testing, and then evaluate the test. So you can see that here we have an accuracy of about 96%. Let's see another important kind of network, the convolutional neural network. The important point is that each node in a layer is not fully connected to the nodes of the layers of the previous layer, but only to a group of nearby nodes. And another important point is that these connections values are the same here, here, here. So since the convolutional neural networks are usually used for images, we often can see these layers like this in 2 dimensions. So this can be seen as filters because they are applied over all the layer. Let's see better here. So this is filter, which is the same filter is applied in all the areas of the image. In this case, we have a 3x3 filter. Generally, we use more filters like this. And generally, each filter tends to specialize to different features. With convolutional neural networks, we usually use a pair of convolutional layer and then a subsampling, pooling layer, which reduces dimensions, taking, sorry. Here. So taking maybe the medium or the max value of grid. So here you can see how we can just changing how we can you can take the example before and just change how to build the network. So in this case, we are adding two couple of convolutional plus pooling layer, but all the other code is the same. And here we have 20 filters here, 50 filters here. So two couple of pairs, convolutional plus pooling. And in this case, and this is the last layer, which is a fully connected layer. And in this case, you can see that the accuracy is higher, is over 98%. So we can also take more complex use cases. This is the Kaggle website. Kaggle websites is usually oriented for TensorFlow and Keras world, but at the end, it contains a lot of dataset that you can use for whatever library. So they do also courses and competitions, but this is a particular dataset about malaria cells images. It contains about 27,000 images of infected and non-infected cells. And if you take the previous example with the MNIST and apply some change, in this case we have 3 channels because we have colored images instead of black and white as previously. And you change something, well, we have changed really, we have made some basic change without any, with the trial. So we had an accuracy of 94%. But this was just an example. So I think that even everyone can do even better with tuning these parameters or adding layers and so on. So here are resources that can be used by you. For example, here you can find the code used in this talk with all the details because the slides were not complete with all the lines of code. And here you have the website of deep learning and the GitHub of deep learning. And here is a very good book about deep learning by Adam Gibson, which is there. We have Adam Gibson here, voice, and John Patterson. So don't forget to evaluate this session, and we are here for questions. We are around for these 3 days, so feel free to interrupt us and ask questions. Do you have questions? No questions? Okay? So, thank you. Thank you very much.